In the last section, we had a number of physical problems or physical quantities that we wanted to estimate the value of. For instance, we had an object moving and we had the velocities of the object at certain times, and we wanted to estimate the change in position. Or we had inflation rates of a balloon in cubic inches per second, and we wanted to estimate the total volume of air that had been blown into the balloon over an interval of time. We had a long rod, a variable mass, and we were given a formula for its mass at different distances, at different lengths along the rod. And we wanted to estimate the mass, and really we wanted to calculate the actual mass from the information about the variable density. We had area under curves, and we wanted to calculate area under curves that aren't just where our formulas for triangles and rectangles don't give us the answer immediately. All of these problems involve the same kind of basic estimation technique, and we want to do the same basic thing, which is chop intervals up into smaller subintervals and take these types of sums we were looking at, the Riemann sums, I'm about to write them again, and see if they approach some limit. We believe physically there's something that's being approached in these examples. There is this physical quantity that we know exists, and surely the Riemann sums are estimating it, and they're estimating it in a better way. Well, they seem to be estimating it arbitrarily closely in our examples anyway, if we take smaller and smaller subintervals. So what did we do? We had a function f defined on a closed interval, AB. And it'll help to picture this. So here's our interval from A to B. What did we do? We chopped up the interval from A to B into lots of subintervals. So we picked a partition, which really is, we specified the x coordinates, or whatever coordinates you want to call them, x, t, u. We chop up the interval from A to B into little subintervals. They don't have to be the same length. Some people like to, or you can pick them all to be the same length. That would give you a partition, but there's x sub 1, x sub 2, x sub 3, x sub n minus 1, x sub n. So you chop up the interval from A to B into subintervals, and in each subinterval we picked a sample point. So in the first subinterval in S1, some first sample point. In the second subinterval, some S2 and S3, and so on. Sometimes we picked, right here I've got the sample points drawn almost randomly. These are kind of to the left of the subintervals, that's to the right, that's in the middle. You can pick sample points that are the left and right endpoints of the subintervals, like this could be S5, S5. And something here, SN. And then what did we do? We looked at these sums. You sum contributions from each subinterval. You take the sum as I goes from 1 to n. You evaluate f at each of these sample points, and you multiply by the width of the ith subinterval. So this is xi minus x sub I minus 1. This is a Riemann sum. And in lots of different problems, this approximates things that we care about. But what we'd like to know, in the examples we did in the last section, and lots of examples that we'll do in the next chapter, in lots of applications, what we would like to know is, yes, that for some functions that are reasonably nice, and we'll get to a theorem that tells us how nice they have to be, for some functions that are reasonably nice, that if you do this process, you take the interval from A to B and you chop it up into subintervals and you take sample points and you calculate Riemann sums and you look at that quantity and you take partitions whose mesh gets smaller and smaller. So the length of any of the longest subintervals gets smaller and smaller. So your partition gets finer and finer. You have smaller and smaller subintervals. That we would like to know that if we take our partition small enough, then regardless of how we pick the sample points, the Riemann sums approximate this quantity that we care about. Volume of air, mass of a rod, change in position, area under a curve. We'd like to know that if we take the partition small enough, regardless of how we pick the sample points, the Riemann sums get arbitrarily close to this quantity. And if that happens, we say that the definite integral exists and that f is one of these functions that we're going to be interested in. So let me make the formal definition. So the definition, this is going to be technical, but I'll try to say it slowly. So we have an f defined on AB. Suppose there exists a real number L. A real number L. Such that, all right, this is going to be the actual thing that we believe exists. So I'll say it again. It's like in our example of change in position, this would be the change from the last section, this would be the change in position. In our example of blowing up a balloon, this would be the change in the volume of the balloon between the time interval, in the time interval that we care about. For the mass of the rod, this would be the mass of the rod. And for area under curve, this would be the area under the curve. It's this quantity that we know exists physically that we're hoping that our Riemann sums are approximating well. And all we're about to define is we're going to say that something is integrable. So has an integral if the Riemann sums, in fact, do approach such a thing. So suppose there exists a real number L such that for all epsilon greater than 0, what is this? Epsilon is going to be how close we say we want all of our Riemann sums to be to L. So what we're saying here is for all epsilon greater than 0. So if someone tells you how close they want all of your Riemann sums to be to L, then you can tell them how small the mesh of the partition has to be to make that happen. And so for all epsilon greater than 0, there exists a delta greater than 0. So this is going to be how small you have to make the mesh of the partition. There exists delta greater than 0 such that for all partitions P, of AB with mesh less than delta, so I'll say such that. And for all sample sets, S for P, the absolute value of the Riemann sum with respect to the partition P in the sample set S of F, the absolute value of the difference between that and L is less than epsilon. All right. I'll say again what this says. We want to say that if the Riemann sums get arbitrarily close to something, that's a case that we're going to call something nice. like integrable. And that is what this says. So this is a suppose. I haven't actually defined anything yet. So suppose there exists a real number L such that you tell me how close you want my Riemann sums to be to L. So you tell me this, and I tell you a delta that would typically depend on epsilon. In really trivial examples, it doesn't have to, but typically it would. I can give you this delta greater than 0 such that for any partition, so if you take any partition at all of AB whose mesh is less than delta, so whose longest subinterval has length less than delta, and no matter what sample set you pick for P, if you take that Riemann sum and you take the difference between that and L, the absolute value is less than epsilon. That's the absolute value being less than epsilon. This is a fancy way of saying the Riemann sum is within plus or minus epsilon of being this L. When this happens, we say that F is integrable. Not a word one says every day. So that's all supposed. Then, if that's true, if there is such an L, then we say that F is, we're only going to have one kind of integral, and that's a Riemann integral. Actually, that's not quite true. When we get to improper integrals, that's not really a Riemann. Those are not really Riemann integrals, but we'll handle them in terms of Riemann integrals. So then we say that F is Riemann integrable. So since we're mainly, essentially only going to have the Riemann integral, we don't normally in this course say Riemann integrable, we just say integrable. There is another very important type of integrability. That's the Lebesgue integral, Lebesgue integrability. We're not going to deal with that. Then we say that F is Riemann integrable on AB and write the limit as the mesh of the partitions approach 0 of the Riemann integral of the Riemann sum with respect to P and S of F approaches L. This L is normally denoted by all right. This L is normally denoted like this. A lot of this should look familiar. If we didn't have the A and B here, this would be our notation for the antiderivative of f of x with respect to x. The reason the notation is so similar is because of the fundamental theorem of calculus that we'll do in the next section that relates anti-differentiation and this, the definite integral, which is what this is called. It's normally it's called. It's called the definite integral of f on the interval AB, over the interval AB. People say different things. On and over are probably the two favorites. I also frequently read it as the integral as x goes from a to b of f of x dx. There are lots of ways of reading this. This is the definite integral. The anti-differentiation is when we're trying to distinguish it from this, it's called the indefinite integral. It's a little confusing. It confuses some issues. The notation's essentially the same for the definite integral and the indefinite integral, and we call them both just the integral sometimes. So it's unclear if someone says, do you know how to calculate an integral, or what does an integral mean? Yeah, if somebody said, what does an integral mean? You could say, well, you might mean the indefinite integral, so an antiderivative of a function, or you might mean the definite integral, the limit of Riemann sums. Which one would they mean? It's hard to know. You'd have to have some more information. All right, I need to make three remarks about this, two short ones and one long one. One remark is, from the definition, it's not clear that you couldn't have more than one L that satisfied that lengthy supposition. But in fact, you can, if there's such an L, there's only one remark, such an L, if it exists. So if F is in fact Riemann integrable on AB, which would mean such an L exists, is unique. There's only one. You couldn't have two different L's with the property that I just erased. If there's one, there's only one. That's good, because that means that this notation specifies one number, not a choice of numbers. All right. Second remark. The x in the integral from a to b of f of x dx is a dummy variable. Now, I mentioned dummy variables earlier when we talked about summations. The index of summation is a dummy variable. It doesn't matter what you call it. And it doesn't matter what you call this either. The integral from a to b of f of x dx is the same as the integral from a to b of f of t dt. It's the same as the integral from a to b of f of u du. It's the same as the integral from a to b of f of giraffe d giraffe. It just doesn't matter what you call this variable. All three of these, and any others that you might write, would mean, they all mean the same thing. You chop up the interval from a to b into smaller subintervals. You partition AB. In each subinterval, you pick a sample point. You stick that value into f. You multiply by the width of the corresponding subinterval, and you add. It doesn't matter what you call the variable. Right? That process is the same thing you do here that you do here. It doesn't matter that it's called t or x or u. Now, in physical problems, this would be a weird thing to do. If you had a problem involving time and you were talking about intervals of time, it would be strange, and you had denoted time by t, it would be strange to suddenly start referring to t as x. In physical problems, you almost certainly wouldn't do that. But mathematically, it doesn't matter what you call that variable. If you want to denote time by x, it doesn't change what you're calculating. All right. The third remark is more serious, or lengthier. Actually, those are pretty serious. This is intuitive. What I'm about to say is not rigorous. It's the way we want to think of the definite integral, and it really does help in many physical problems to think of it this way. So what we've just said is the definite integral from a to b of f of x dx is, well, it's a limit as the mesh of the partition approaches 0 of Riemann sums. But a Riemann sum looks like this. So if such a limit exists, and the exact meaning of this limit is what I defined before, if such a limit, the number L, if such a limit exists, we say that this integral exists. F is Riemann integrable, and this is our notation for whatever this limit is. So how does that mean you should think of all the pieces in this notation? Well, the delta xi, you should think the delta xi is becoming dx. Now, what do I mean? Well, what's really happening, the mesh of the partition is approaching 0. All of these delta xi's are approaching 0. They never are 0, but they're getting arbitrarily close to 0. So you should think of this as a delta x that is arbitrarily close to 0. So we usually think of this, or frequently think of this, as an infinitesimal change in x. We think of it as kind of the limit of the delta x's. Now that's not right, because the limit of the delta x's would be 0. But it is helpful to think of this as an infinitesimal change in x. This is not rigorous. This can be made rigorous. There is a way of looking at calculus called non-standard analysis, in which they make formal use of infinitesimals, and that's their approach. Instead of using limits, they actually use serious infinitesimals. We won't do that, but we will think intuitively of this as an infinitesimal change in x. This is just the value of the function at a point x. And what is this? How should you think of this integration symbol, which is a curly s for summation? It's a fancy s for summation. So this integration symbol and the a and the b, well, that's just telling us it's kind of what the sum becomes. Right? It means add up these things. Well, what are these things? Well, if you take f of x at an x value, this is just a number. At any x value between a and b, this is some number. When you multiply times dx, well, suddenly you should think of it as an infinitesimal quantity, because maybe this is 5. 5 times something infinitesimal, you should think is still infinitesimal. If this sounds kind of like hand-waving and like it shouldn't mean anything, right, I'm telling you this is kind of how you think of it. And I'll do some examples, and hopefully it'll be more clear how you think in this way. Rigorously, we're taking limits of Riemann sums. But it's helpful to think of it as, you pick an x, you take f, you evaluate f there, you multiply by an infinitesimal change in x, and this gives you, maybe in some problems, an infinitesimal change in area, or an infinitesimal change in mass, or an infinitesimal change in volume. And then you think of this as a continuous sum of all of these little infinitesimal changes in these quantities. So this is a continuous sum of infinitesimal contributions. So, for instance, if this corresponded to an infinitesimal little change in area, then you would take a continuous sum of all these infinitesimal little areas as x goes from a to b. Well, then you'd get the whole area under the graph from a to b. Or if you had an infinitesimal little chunk of mass, and you add up all the infinitesimal little blobs of mass between x equals a and x equals b, then you'd get the total mass of a rod, for instance, which is what we're going to do in a minute, between x equals a and x equals b. Let me draw the number line. I drew the interval from a to b on here before and partitioned it. Right, that is what we're doing, and you should keep that in the back of your mind. But when you're thinking of things like this, and you don't want to write partitions, and you don't want to write sample sets, and you don't want to write summations, you don't want to write limits, the way to think of it is you look at the interval from a to b. You pick at each x coordinate. Now, what do I mean at each x? Why am I about to say something about what happens at each x coordinate? As the mesh of your partition approaches 0, your sample points become arbitrarily close to any given point. Like if I picked anything between A and B, if our partition's small enough, then one of the sample points has to lie in the subinterval that contains x, and so it has to get arbitrarily close to this x. So, yeah, in the limit, you think, oh yes, we calculate something at each x coordinate. And what is that thing? Well, you think you take your x coordinate, and then you take an infinitesimal subinterval around it. So something of width dx. Now I can't draw it infinitesimally small. If I drew it infinitesimally small, I wouldn't see it, you wouldn't see it. But so I'm drawing it big, but you should think of this as being arbitrarily small. And then here where we have f at the sample point times delta x, instead you think of f of x times this infinitesimal dx. And then you add these up continuously as x goes from a to b. So this is how we're going to talk about the definite integral in a number of applications, especially in the next chapter. And we'll keep in the backs of our minds that we're actually taking limits of Riemann sums, but we'll talk about it like this often. All right, well, let's look at this in a couple of examples. Like, let's go back to our rod of variable mass, variable density from the last section. So, example. We could be slightly more general than we were in the last section. It's not. We had a rod that was 1 meter long, but I don't care that it's 1 meter long. It could be any length. I will start it at 0, but I'll just go out to some length L. And I will give myself an x-axis here. I'm assuming it has some cross-sectional uniform area. I'm going to call that A. A equals the constant cross-sectional area. Before it was 0.01 square meters, but now I'm just going to say it has constant cross-sectional area. Yeah, we'll still measure this in square meters. So. And we assumed we had a density function. So in that example, it was 1 plus x. This was kilograms per cubic meter. So this was the density at coordinate x. What do I mean? I mean that if you take an x coordinate, in that example, we were assuming that if you take the cross section at x, so you take a perpendicular slice to this rod at x, first of all, the cross-sectional area at that x is this constant a, but we're also assuming the density of the rod at each point in that cross-sectional area is the same, so that the density really does just depend on the x coordinate. So I'm assuming the density in kilograms per cubic meter, mass per volume, the density in kilograms per cubic meter only depends on x, and we're told the dependency. Its density is 1 plus x. Then how would you estimate the mass of the rod? Pretending we knew how to calculate integrals, so how would you write the mass of the rod as an integral? You'd think in the following way. Here's the density at this coordinate. We take an infinitesimal little change in x. So here's x. Put x there. Put a dx here. We take an infinitesimal little change in x here. Again, I'm not going to draw it really small because then you wouldn't be able to see it. But you should think of this as a very small change in the x-coordinate. We're going to estimate the amount of mass in this little chunk. So what's the mass of this infinitesimal chunk? So it's density times volume, but the density is variable. But here's where our infinitesimal approach is nice. Well, yeah, the density is variable, but there's really only one x-coordinate in this interval because it's infinitesimally long. There's not another one to talk about. So dm, the infinitesimal amount of mass over this infinitesimal subinterval it equals the density times the volume. The density is delta x, and the volume is the cross-sectional area, A, times the length. But the length is the infinitesimal dx. If you're going to have an infinitesimal on one side of an equation, like this, you better have an infinitesimal over here somewhere. So we really do write this, that dm, an infinitesimal little chunk of mass, or if you want the change in mass, if you're measuring total mass starting here, it would be the change in mass from here to here, because you would have the total mass out to here and subtract the mass here. So you could say the change in the total mass. But the infinitesimal little chunk of mass that lies over this subinterval, dx, is delta x times A dx. Well, how do you get the total mass of the rod? You add up all these infinitesimal little masses as your x-coordinate goes from 0 to L. So the total mass of the rod, in integral notation would be the integral from 0 to L of 1 plus x, put in what delta, actually I'll write that in another step, of delta, let me try this again. So I'm going to write more steps than I was going to write. So total mass, the mass of the rod, it's the continuous sum of all of these infinitesimal little blobs of mass as your x-coordinate goes from 0 to L. I've added some notation here. I wrote x equals 0 to x equals L. That's because there's a dm here. And in our notation for the Riemann sums and the limit of them turning into the integral, the numbers we put here, the a and the b, we're supposed to tell you what m does, that m goes from a to b. If that's not the case, if some other variable is going from a to b, like x is going from 0 to L, and you still want to talk about this continuous sum, some integral, then you have to write that, yeah, I don't just want to put 0 and L here, because I'm not saying that m starts at 0 and goes to L. I'm saying x starts at 0 and goes to L, but as that happens, we want to add up all of the little m's. So you have to explicitly write x equals. And then, yeah, this is, you put in that dm is this, and delta x is 1 plus x. And you get a dx, and now x is going from 0 to L. So yes, this definite integral is what we want to calculate to find the total mass of this rod. Now, really, this is how you want to think of it. It's a limit of Riemann sums. Yes, we're really chopping the interval from 0 to L up into lots of little subintervals. And then we take a sample point in each subinterval, and we write delta at SI times A times delta XI. And that only gives us an approximation to the amount of mass that's in there. So you'd write approximately equal and a delta M. And then you'd sum up all of those and you'd get an approximation to the total mass that you intuitively, physically know approaches the actual mass of the rod as you take smaller and smaller partitions. So partitions, well, I shouldn't say smaller and smaller. As you take partitions with arbitrarily small mesh, you expect this approximation of the mass to actually approach the total mass. All right, I should say, and I should have written this in the definition before, the A and the B that are here are also referred to, you don't just say over the interval from A to B. If we want to refer to these numbers kind of separately, these are also referred to as the limits of integration. In fact, let me not try to cram this in over here. Let me put it over here. So, yeah, more terminology related to the notation. The integral from A to B of f of x dx. The function itself is frequently referred to as the integrand. And the A and B are frequently referred to as the limits of integration. Okay, I want to look at this kind of infinitesimal way of viewing things for area, because this is going to be our primary graphical way of looking at integrals. So let's take another example. We looked at area in the last section, but now I want to talk about it in terms of Riemann sums, but also in terms of kind of this infinitesimal description. So suppose you've got some function, and here's part of its graph, and I'm going to assume, as I've drawn it, that f of x is greater than or equal to 0, at least on the interval that I care about, so between a and b. So what we saw in the last section was that the limit of Riemann sums approaches the area under this curve and above the x-axis. So that this area, the area under this curve and above the x-axis would just be the integral from a to b of f of x dx, provided the integral exists, right? Provided f is integrable. Right? Not all functions are integrable, and I do need to give you a theorem that tells you some important functions that are integrable. But yeah, assuming f is integrable, that area would just be the integral from a to b of f of x dx. In this infinitesimal kind of point of view, the way you would draw that would be that you would pick some point x, and then you, once again, give yourself some infinitesimal little interval around x. And then you look at the corresponding, I'm going to call it a rectangle, but you look at the corresponding rectangle, except does it curve or not? The answer is, well, first of all, we're talking intuitively, so it doesn't really do anything. But this is an infinitesimal change in x. We don't really view this height as different from this height. We do think of this as being a rectangle. Its height, what's the height of the rectangle? Its height, if this x-coordinate is x, this height here's our rectangle. It only looks like it curves at the top. This height is f of x. right? It's the value of f at this x-coordinate. Well, what about the heights at the other x-coordinates? Again, we're thinking of an infinitesimal interval. There are no other x-coordinates in there. And so you think, oh, okay, so this is some infinitesimal little rectangle. What's the area of this infinitesimal little rectangle? We write dA for dA, an infinitesimal piece of area. So, and then, what do we write? Well, what's the area of a rectangle? It's the height, the f of x, times the width, the dx. So f of x times dx is the height times the width, and this should be this infinitesimal little chunk of area. Again, if you have this infinitesimal quantity over here, you better have, or since we want this infinitesimal quantity over here, you better have an infinitesimal quantity over there. I'll say it again, of course, really, we could do Riemann sums. You really are, the approximate change in the area is f at some sample point times the width of a subinterval, and then you add things up after when you had a partition. But this is how you want to think of it. And so what's the total area under the graph above the x-axis? So above the interval AB. Well, it's the continuous sum of all the little blobs of area as x goes from A to B. So you take the continuous sum of all of these little chunks of area, and it gives you the total area as x goes from A to B. So then you put in that dA is f of x dx. And so what you get is the integral from A to B of f of x dx. Right. Right. So the definite integral, at least for a positive function or a non-negative function, our main graphical interpretation of it will be that it's the area under the graph and above the interval. I do want to say what happens if the function becomes negative. Then how do you interpret things in terms of area? So let's take an f that does this, and maybe A is over here, and B is over here somewhere. This is the graph of y equals f of x. What are we going, how can we interpret the integral in terms of area here? Let's call this C. It's not going to be important to us really what it is, but let's just call that point C where the function switches from negative to positive. Can you still interpret the integral from A to B of f of x dx in terms of area? Right. And the answer is yes. You can, and you have to think about it. When you're over here, so when your x-coordinate is between C and B, so when your x-coordinate is somewhere over here, yeah, you do what we just did. You're at some x-coordinate, you take an infinitesimal subinterval of width dx. The height of this infinitesimal rectangle is f of x. And so this, you get this little chunk of area is f of x dx. And yes, at least from C to B, the integral would calculate the area under the curve, as we know that it would, because if we just did our definite integral that we had before, we'd just get the integral. If we treated this like a, then f of x, like if we treated this like a before, f of x is greater than or equal to 0 between here and here. And so we know that this area, let me call this a sub 1. Actually, I'll write a sub cb. So the area over the interval from c to b, that area would be the integral from c to b of f of x dx, provided f is integrable on that interval. But what about this? There's some area here below the graph. So there's some area here. Area is a positive quantity. But our function is negative, and certainly our chunks in the Riemann sum that we would get in the Riemann sum, or that we would get thinking about it infinitesimally, would also be negative. Right? Because if you take an x-coordinate here, and you look at an infinitesimal rectangle that has an infinitesimal subinterval around that x-coordinate, then f of x dx, so over here, when we're between a and c, so let me write, this was for x between c and b. That dA is f of x dx, but for x between a and c. For x between a and c, what do you get? Well, f of x dx, f of x would be negative. So it's not a height. Negative f of x would be the height of this rectangle. F of x is negative. So this distance right here, this distance, so this height, is negative f of x, right? Because f of x is a negative number over here, so negative f of x is this height, and it'll be positive or greater than or equal to 0. So this area, the area under the graph, or sorry, above the graph, this was the area under the graph and above the interval from c to b. This is the area over the graph and below the interval from a to c. This will be, well, once again, it's the sum as x goes from a to c of all the little chunks of area, just like it was before. But now, the little chunks of area are negative f of x, the height, times the width. So negative f of x times dx. All right. So we have this minus sign. Now, an integral is a limit of sums, and if you have a sum of a bunch of negative quantities, you can pull the minus sign out. This is the same as negative the integral from a to c of f of x dx. So, what did we just conclude? We concluded that if we have this A, we have this C, we have this B, here we have this area, the area under the curve and over the interval from C to B. Here we have this area, the area, so under the interval from A to C, but over the curve, what we just found is for this part, yes, the integral gives you the area, the integral from C to B of f of x dx is in fact that area. But what we found for this part over here is that negative the integral from A to C of f of x dx is the area under the interval from AC and above the graph. If we put the minus sign on the other side, what we get is this. And this is important. This is, yes, if f of x is positive, then if you want to picture the integral from C to B, so if f of x is positive between C and B, and you want to picture the integral from C to B, you picture it as the area under the graph and above the x-axis. If f of x is negative, like it is between A and C, and you want to picture the integral from A to C, you picture it as signed area. Area has to be positive or greater than or equal to 0. So the area under here is not negative, it's some positive number. But the integral, if f is negative, this is, remember, it's a limit of Riemann sums. If x is negative, if f of x is negative, this is going to be negative, or less than or equal to 0. Where actually, if f of x is negative, this is going to be negative. But, so it better come out to be a negative number, but the area, this area is positive, so negative the area would be negative. So to interpret the integral in terms of area, it's area above the curve counts with a plus sign as far as the integral is concerned. Area, Area below the curve counts with a plus sign, below the curve and above the x-axis. Area below the x-axis and above the curve counts with a minus sign, like it does here. I am absolutely not saying that area is negative. I'm saying that if you want to interpret the integral from here to here in terms of area, it's negative whatever that area is. All right. This section is a long section. I haven't finished saying all that I need to. I want to give a bunch of properties of definite integrals, and not many more physical examples, but a bunch of properties of definite integrals, and calculate a few of them by looking at the area interpretation using formulas you should know for area. But we'll do that in the next lecture.